This is going to be a video about geometric series and basically how this relates to power series. So the first thing we're going to do is we have our definition of geometric series right here. Series just means you're summing up a bunch of numbers, and it's in the summation notation. The sigma right here just means adding up each of these as n goes from 0 in this case to infinity up here. Okay, so how this would look if you wouldn't be able to go to infinity, but if you wrote these out, it would be AR. Now the n is 0 at first, so I'm going to put AR to the 0 here, which just cancels out. It's just going to be A, but it's okay. Let's keep going. Plus AR. Now after 0, we go to the next integer, which is going to be 1. And the n's are basically just changing. Now the reason the n's are changing is because of how this is defined right here. There's an n here, and n's going from 0 to infinity. You get the idea. So here we go, AR to the third plus, we're running out of room here since we're going to infinity. So what we're going to do next is I'm going to put dot, dot, dot here. We're going to be adding these up. Just imagine these keep going until you get to AR to the n. But then after that, we're still going to infinity. So you're still going from there. Okay, so you have something like that for a geometric series. Now, a really interesting thing and very clever thing that you can do with geometric series is I am going to set this first part equal to S. So I'm going to say this whole thing is equal to S, S for sum. Okay. And what I'm going to do with this S is I'm going to multiply it by R, which is the same R that we have right here. And if we multiply R by S, you would get AR to the first, because you're just multiplying every single one of these by R. So if you multiply this by R, that 0, you can just add 1 to the exponent here to get AR. AR times R is AR squared. AR squared times R is AR to the third. AR to the third times R is AR to the fourth. You get the idea. Dot, 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 plus, this one's going to be AR to the n plus 1 plus dot, dot, dot. So I'm just basically linking these S's and the RS together for each of these. All right, let's keep going down the rabbit hole a little bit further. All right, so way back in the day, someone would thought it was cool if we could take S and subtract it from RS. Okay, if you're wondering why I'm doing all this, it's eventually to get to a specific result. So if you're like, why is he multiplying the S by R? And then why is he subtracting S by RS? It'll make sense when we get to the end here. So just bear with me. I promise this will be a cool result. All right, so S minus RS. Okay, if you notice, you can't just subtract term by term here from what directly is underneath it, because it doesn't match. You can't subtract unlike terms, but what you can do is you notice this AR to the first and this AR to the first, those would cancel because it's S, this is S minus RS. That means this and this would cancel down here. Okay, this would stay right here because there's nothing to cancel with it. But if you notice, every single one that we go down here is going to cancel with the next one. Now I put dot, dot, dots, but you can kind of just imagine those in your head. So that means that S minus RS gets a really crazy result here. So it's going to be AR to the 0, which is just A, because R to the 0 is going to be 1. So I'm just going to say that's equal to 1. Okay. All of these other ones are going to cancel here, but you're going to be left with this one right here, this AR to the n plus 1. Now, n is going to infinity. It is really important to understand that. So I'm going to do A plus the limit as n goes to infinity for AR to the n plus 1. Now, if you might be wondering, where did the AR to the n go? Well, it was directly before it, just like these other ones, like this one were before it, this one and this one, this one and this one. If you kept going, the AR to the n is in this dot, dot, dot part. It would cancel with this one here. So these would match up. So if you're wondering where that goes, this one would not, because it's going to infinity. It's just never going to be able to catch it. So you end up with this, what I have in this green right here. Now, an interesting thing that you can do here is you can factor out an S, and you get S times the quantity 1 minus R is equal to the same thing that we just had here. From here, we can actually solve for S, which you might be thinking, we already solved for S, it's up here. We solved for S right here. But this is a little different result. That's basically why I'm doing this. So what I'm going to do here is divide both sides by 1 minus R, and you're going to end up with A over 1 minus R plus this whole thing right here divided by 1 minus R. Okay. Now, a very interesting thing happens with this limits right here. So we're going to kind of pay a little bit of attention to this first. So I'm going to take this part right here and just kind of work on it down here. We will get to that a over 1 minus r in a little bit, but just for right now, just keep paying attention. This gets pretty cool. So if you had r is equal to 1, you would be dividing by 0. So if you tried plugging this in right here, it would be 1 minus 1 on the bottom. And so this limit would end up just being undefined. Okay, that's not very exciting. Let's keep going though. What if r was greater than 1? Okay, if r was greater than 1, you're going to have a negative on the bottom. That's not really that serious. If it's greater than 1 up here for the r, and n is going to infinity, so let's just say the r that's greater than 1 is 2. If it was 2 to the infinity power, it doesn't matter what this a, well, it does matter what this a is. If the a is negative, you're going to end up with negative infinity. If it's positive, you're going to end up with positive infinity. So I'm going to write positive or negative infinity here. Okay, so if r is greater than 1, it's going to be positive or negative infinity for this limit. Now, if r was less than negative 1, the same thing is going to happen because it's similar to the one we just did with the r is greater than 1. If you plug negative 1 in here, it could be made positive by this term right here. Furthermore, if you have a r is equal to, let's just say it's negative 2, negative 2 to the infinity isn't even an exponential function because you have a base that's negative. Either way, we're just going to say this is undefined just so we don't have to worry about it for right now. Moral of the story is you're not going to get any result from that. So let's not worry about that right now. But an interesting thing is going to happen if you take r less than 1, but also greater than negative 1. So it's between 1 and negative 1. We can't plug in 1. We could have tried plugging in negative 1. If we actually plugged in r equals negative 1, you're going to also have an undefined, because if you plug negative 1 as the base, as you increase the n here, it's going to be going all over the place because you have a negative base on the exponent. And I can show you that more in class, but we don't really need to worry about it. The main thing we do need to worry about is when r is between negative 1 and 1, which is what this is saying right here. Okay. If it's between negative 1 and 1 and you're going to infinity, that limit ends up just being 0. Okay. And let me show you why. Let's just pick a value. Let's just pick r is equal to 1/2 because 1/2 is between negative 1 and 1. I guess 0 would have been easier, but let's pick 1/2 to be more fun. If you did the limit as n approaches infinity of a, now I'm going to put the a in front because it doesn't have anything to do with this n going to approaching infinity. I'm actually going to put this 1 minus r in the front as well, just to make it easier. And then you end up with r to the n plus 1. Now I said r is 1/2 for the example that we're using. If r is equal to 1/2, you're basically going to have 1/2 to the infinity power. Okay, 1/2, if you just keep multiplying it by itself over and over and over and over and over and over and over again, eventually you're going to get 0, which is what we talked about right here. Okay, anything that's between negative 1 and 1 is going to be a decimal number or a fraction number. It's going to be between negative 1 and 1. And it's always going to lead to this whole thing right here just going to 0. Okay, again, this is if r is between negative 1 and 1. So an interesting thing happens here. This is where we get to the super exciting part here, is s is equal to a over 1 minus r. So it's a very simple, very basic expression right here. This very simple and basic expression is equal to an infinite sum. So if we add something up infinitely many times, it's still equal to this very basic rational expression, but it's only if you're on the interval from negative 1 to 1, okay? This negative 1 to 1 interval for geometric series is called the interval of convergence. This interval of convergence is always based on whatever the r is and making sure that r is between negative 1 and 1, because that's the only time where this is true, which is really crazy to think about. Something that you're adding up infinitely many times is actually equal to, if you just took that same a that's in each of the problems, the same r, and you just did a divided by 1 minus r, it's equal to if you added things up infinitely many times. So you might be thinking, yeah, right, that makes no sense. I don't believe it at all. I'm actually going to show you right now using a graph. All right, so we have a graph right here, and I am trying to show that if I had some function that was a divided by 1 minus r. Now, I can't use r in this case because our function is defined with an x, so I'm just going to make this an x for fun. The r is the x. It doesn't matter. A variable doesn't matter which variable you use. It's going to still work out. A is going to be our constant. We're just going to say it's equal to 1. Now, if you graph this, it ends up looking something like this. Now, a can be anything, so you do have infinitely many graphs because a is just a constant, so any of these graphs would work that I'm having here. This just for our purposes, let's just make it 1 so it's easier. Okay, now I'm going to see if f of x is equal to g of x. Now, g of x is going to be equal to what I was talking about before with the geometric series. We have 1 plus x squared plus x to the third plus x to the fourth. Now, I said that this f of x function should be equal to the g of x function. The problem is the g of x function is really supposed to go to infinity. We can't go to infinity. As you can see right here, it's giving me a little error here. You need something after it. Okay, but you can kind of see the pattern that is, as I'm adding more and more of these terms, you're getting closer and closer to being directly over that f of x function. And if you notice, the interval that it's directly over is between -1 and 1. Let's blow this up a little bit here. So if I had where it's -1 to 1 for the original function, you can see that it's getting really close between -1 and 1. That's the only intervals that we actually care about for this function, because that's the only intervals where it's going to converge. All the other ones, it's going to diverge and go off to infinity or -infinity. Now, let's just say you still don't believe me. What I did, rather than having to write all these in, because it's going to take me a year, I made a Python program. So I have a Python program here that I made, and basically you don't really need to understand the code for it. You just need to understand what it does. You can input how many terms you want. So I just wrote a 10 here, and it basically prints out the LaTeX code that's needed for that geometric series. So say I wanted 10 terms. If I run this, it actually prints it out down here with 10. So I can just basically take this right here. So I can take that code and paste it in to Desmos. And you can see that when I go to 10 terms between -1 and 1, basically that green function is right on top of that red very, very well. So you might be thinking, what happens if we even use more terms? Well, technically, if you use infinitely many terms, then it's going to be the exact same thing between -1 and 1. But just for fun, let's up the number of terms. All right, let's just say we want 50 terms. Okay, if I run this, it's going to be a crazy amount of code here. I copy and paste this into Desmos. All right, so I'm going to paste that code from the Python program right here, and it takes a little bit to finally graph it out because it has to go through all 50, but there you go. And as you can see, between -1, let me zoom in here, between -1 and 1, hold on, let's do this. 1, let's get rid of the grid. We don't really need that. But you can see between -1 and 1, pretty much right over it. Again, you can't include -1, you can't include 1 on it, but in between it should be right over it, and that's with 50. And you might be thinking, great, we figured out a way of getting a power series, that geometric series. We figured out a way of getting that to represent some function of a over 1 minus r. What's the big deal with that? Well, the big deal of that, and we're going to explore this in the next video, is that you can turn basically any function into a power series, which has tremendous implications. Namely, certain things you can't find the antiderivative of it directly, but if you use power series, you should be able to find the antiderivatives really no problem, because you just need reverse power rule for these types of problems just because it's a polynomial. And there's other applications that you can use as well that we're going to explore in the next video, but just try to wrap your head around it. The fact that we have this simple rational expression right here, and it could represent an infinite series. Okay, so we have an infinite series adding up infinitely many numbers, but it can be represented by this finite rational expression. Again, you have to mind the interval of convergence for it, but still very powerful. We're going to talk more about interval of convergence later as well. So that's basically a video on geometric series. If you have any questions about anything in this video, let me know.